Recently, I came across a very interesting study that explains the accelerated expansion of our universe in a very elegant way by the absorption of other baby universes into our own without the necessity to use any dark matter, dark energy, or anything of the stuff that nobody knows what it actually is. As most of you might know, in 1998, two independent research teams studying Type 1a supernovae made a discovery that would earn them the Nobel Prize and fundamentally challenge our understanding of the cosmos. Saul Perlmutter, Brian Schmidt, and Adam Riess found that distant supernovae were dimmer than expected, indicating that the expansion of the universe was not slowing down due to gravitational attraction, as it had been assumed, but was actually accelerating. This observation was revolutionary because it contradicted the basic expectation that gravity should be slowing cosmic expansion. Since the Big Bang, we expected the universe to expand, but at a decreasing rate due to gravitational attraction. Instead, observation showed that expansion began accelerating approximately 5 billion years ago, suggesting the presence of a repulsive force stronger than gravity on cosmic scales. To explain this acceleration, cosmologists introduced the concept of dark energy, a mysterious form of energy that comprises approximately 68% of the total energy density of the universe. The standard ΛCDM model incorporates this as the cosmological constant, representing a constant energy density field filling space homogeneously. However, the physical nature of dark energy remains completely unknown. That's why we call it dark, as we have no clue what it actually is, making it one of the most significant unsolved problems in physics. The Hubble constant, which means the current rate of cosmic expansion, has been determined through multiple methods, yielding values around 67 to 74 kilometers per second per megaparsec. However, different measurements techniques produce systematically different results. Right before we dive into today's exploration of that new interesting 2023 study, I need you to please do me a favor. Hit that like button if you find this content valuable, subscribe for more in-depth scientific analysis, and let me know in the comments where you're watching from. I'm Martin, currently enjoying the summer here in Cape Town, South Africa, where I'm escaping the German winter while contemplating the deepest questions of cosmic evolution. In the December 2023 edition of the Journal of Cosmology and Astroparticle Physics, that's my dog, Jan Ambjørn from the University of Copenhagen and Yoshiyuki-Watabiki from the Tokyo Institute of Technology published a groundbreaking study in the Journal of Cosmology titled "Is the Present Acceleration of the Universe Caused by Merging with Other Universes?" This work proposes a radically different explanation for cosmic acceleration that eliminates the need of dark energy entirely. The central hypothesis of their model is that our universe exists within a multiverse framework where it continuously merges with smaller baby universes. These merger events add volume to our universe, creating the observed acceleration without requiring any mysterious energy component. You can imagine it like our universe being a big water drop, small water drops dripping onto that big water drop and thus expanding its volume. So obviously other water drops are merging. You wouldn't know why, but you would see, okay, the surface is expanding and experience and observe an increased speed. Speed is increasing of expansion if you just were to sit within the middle of that water drop. But where did all these baby universes actually come from, you might ask, without knowing that, well, in the Watabiki model, the creation of baby universes is a way to explain how space itself grows and why the universe expands. At the very beginning of our universe, there was a mother universe with a fixed initial volume. Think of this like a primary drop of water. This liquid contains all the potential for space and matter. Due to quantum fluctuations, tiny random energy spikes, the surface of this liquid starts to bubble. These bubbles are baby universes. In the theory, the expansion of the universe isn't just space stretching. It is the continuous creation of these new tiny units of space, these baby universes as we call them. As more baby universes are born, they add to the total volume, making the drop larger and larger. This is basically the other way around. In the early stages of the universe, when it was small, the surface tension and internal forces are strong. This pulls back on the expansion, which is why the deceleration parameter starts as a positive number, slowing down. And in the later stages, as billions of baby universes are created, the internal volume becomes massive. The outward pressure of these new units eventually wins. This is why the universe's expansion eventually starts to speed up and Q becomes negative. Why babies? Well, the term is used because each of the new units of space inherits its properties from the parent liquid, but becomes its own distinct part of the fabric of spacetime. The total size of the universe at any time is simply the original mother plus all the babies. And why do I like the merger model so much? Well, because it comes along without any stuff that we don't know, like dark energy, dark matter, dark something that we call dark because we have actually no idea what it is and what it looks like.
No dark matter! No dark energy!
And it offers a potential resolution to the discrepancy in Hubble tension between the early universe and nowadays universe. That means the merger rate model offers a potential resolution by allowing the expansion rate of the universe to vary based on merger history. If our local cosmic environment experienced different merger rates than the global average, this could explain the observed discrepancy without requiring new physics with a standard model framework. So what would be the broader implications for physics if we could actually confirm the merger model? Well, it would provide strong evidence for discrete approaches to quantum gravity, like CDT over continuous approaches. Concerning the multiverse physics, it would establish the multiverse as a physically relevant concept rather than a purely theoretical one. The assumption of homogeneity on large scales might need revision if merger effects create preferred directions or regions. Question about information preservation during universe mergers could provide insights into quantum gravity and black hole physics. Finally, the Ambjørn-Watabiki merger model represents a paradigm shift in our understanding of cosmic acceleration. By replacing the mysterious dark energy with a geometric process of universe absorption, it offers a potentially more fundamental explanation for one of cosmology's greatest puzzles. While the model faces significant theoretical and observational challenges, it makes testable predictions that distinguish it from the standard ΛCDM model. The next decade of observations of the James Webb Telescope, Euclid, and other advanced instruments will provide crucial tests of these predictions. Whether or not the merger model proves correct, it demonstrates the importance of considering radical alternatives to established paradigms. Well, whether the merger model actually proves correct or not, it demonstrates the importance of considering radical alternatives to established paradigms. The history of science shows that most profound advances often came from questioning of our most basic assumptions of the nature of reality. Last but not least, you could explain the merger model with that droplet scenario to a 4-year-old. It might get a grasp of what you're talking about. Well, good luck trying that with standard quantum gravity.